today. We're happy to have Yoav Gatso from Tel Aviv University talk about third division via resource augmentation.
Yes. Okay, hi everyone. So thank you for the organizers for having me and for this great day. Continuing with the third division theme from the last lecture, I will be talking about third division via resource augmentation, and this work is a joint work with Hannah Krami from Bonn University, Alon Eden, Michal Feldman, and Amos Fiat. And the third division problem is as presented in the last lecture. So what we have is a set of agents. So here are the animals and the goods, which are the fruits, and we would like to partition the goods among the agents such that the allocation is fair. And for that purpose, we assume that we have the valuations of each of the agents to each subset of the fruits, but obviously we need to ask what is fair. Okay, we need to define fairness in order to talk about the problem in a formal manner.
Oh, so it's not additive.
Sorry?
It's not additive, it's for each subset.
For now, yes, we will consider general valuations as well in this stuff. Yeah, I will define everything shortly. So roughly speaking, fairness notions come in two flavors. One is envy-based notions, in which an allocation is fair. The definition of fairness also depends on what other agents have received in the allocation, whereas share-based notions, which is what the focus of this talk, is where the fairness of an allocation in the eyes of an agent is only determined by the value of the bundle that he got and also the number of other agents in the setting. So formally defining the problem, we're given a triplet. So N is the set of agents, M is the set of indivisible goods, and we also get a monotone valuation function. So this function describes for each subset of the goods what is the nominal value for this agent. And as a special case, and for most of the talk this will be our focus, we'll look at additive valuations, where the valuation of a set is simply the sum over the valuations of each item in the set. And what we're looking for a fair allocation. An allocation is the partition of the goods into n bundles such that agent I gets bundle AI. Okay, so I have yet to define what fair means, but we're looking for a fair allocation. Here's an allocation. Okay, so let's talk about share-based fairness notions. So a share-based fairness notion is defined according to some threshold. So each agent I has some individual threshold, and we consider an allocation fair in the eyes of agent I if the value for the bundle he receives exceeds this threshold. As I said earlier, this threshold may depend on the number of agents in the setting. And maybe the most intuitive share-based notion is the proportional share, where we call an allocation fair with respect to the proportional share if each agent gets 1 over n fraction of what he values the entire set of goods, or the grand bundle. One can see that in this setting, right, when we have two agents, the alligator and the bear, and just one good, one indivisible good, the blueberry, a proportional allocation may not exist, right? If both the bear and the alligator value the blueberry with non-zero value, only one of them can get the blueberry, so one will have to get a bundle that is worth 0. So proportional allocation may not exist. In 2011, Budish have introduced a new share-based notions for fairness, which is the maximin share, which Alon already defined in the last lecture, but for completeness, maybe I'll just repeat the definition quickly. So it is determined by the following thought experiment. We let agent I partition the goods into n different bundles, and we assume that he gets the worst one from his perspective. And the value, so the MMS value is determined according to the partition, which maximizes the value of this bundle. So the partition of all goods into n bundles that maximizes the value of the minimal value bundle. Okay? So note that here in this 2 agents, 1 item example, the MMS share is 0, right? because the only way to because every partition of one good into two bundles must have an empty bundle. So the bear here gets his max-min share even though he does not get the proportional share. And as a side note, for additive valuation, the proportional share is always greater, weakly greater than the MMS. Okay, so max-min share, also known as MMS, or using both. Okay, this might not be as entertaining as Alon presented it, but still, let's get one example for what is MMS. So we have an additive valuations here. Each of the agents values each of the fruit with the number mentioned in the proper cell. And what is the MMS of the alligator? This is the partition which maximizes the minimum value of a bundle. Here, the apple, the banana, and the apricot belong to one bundle, the pear and the blueberry to the other. Both have a value of 7. His MMS is 7. Believe me, there is no other partition which has a greater minimal value bundle. The bear has an MMS of 6 because this is the partition that maximizes the minimal value. And an MMS allocation, again, is partitioning the fruits into two bundles, giving each of the agent a bundle, such that the value of the bundle exceeds the MMS of both players. So here, the bear gets exactly one of his MMS bundles, which is worth 6, so that's valid from his perspective. The alligator gets much more than the MMS, right? He gets 3 fruits, he values them at 10, but his MMS is 7. Good. Okay, so I guess there are no more questions about how MMS is defined because you would have asked them in the previous lecture. So, as Alon mentioned, an MMS allocation may not exist. This is known since 2014 for even for additive valuations, and there is also the Feiges-Sapir-Tauber from 2021 that show that even for 3 agents, there are instances in which one agent may not receive his MMS. In light of these impossibilities, there are many types of relaxation that can be done. So Alon just showed one where you change, where you get prediction for the valuations, but the most studied relaxation is the approximation lens, which Alon has also discussed, and this is receive alpha MMS. So what is the alpha MMS relaxation? We call an allocation alpha MMS if it guarantees each of the players at least alpha fraction of their MMS value. And I noticed Sergio is not here, but in this talk, alpha will be smaller than 1, not really. So I'm sorry. Yes.
Say it again.
Yes.
Record.
Alpha fraction. You can. I even highlighted alpha fraction. No. This was intentional. I'm actually in the. Yes. I'm actually in the alpha smaller than 1 camp. I don't know. Maybe me and Sergio are the only ones there. I don't know. Okay. So yeah, this alpha approximation is really well studied. So there's a long line of work trying to find the largest alpha such that an alpha MMS allocation always exists. Particularly for additive, there is a long line of work improving the upper bounds and showing lower bounds. So the best we know now is just a little bit more than 3/4. This is due to Karami and Garg. This is the best upper bound that we currently know. There is a lower bound, again, due to Feiges-Sapir and Taubel, of 1 minus 1 over n to the 4th, so we cannot get a better fraction than this.
Still mix upper bound and lower bound.
Sorry? Okay. Okay, so for additive there is a really long line of work. Also for beyond additive, there are numerous results which I'm not going to get into. Maybe I'll just point that for monotone valuations, or general monotone valuations, not in the complement-free hierarchy, like the largest class in the complement-free hierarchy, there is actually a very simple example to show that this is inapproximable. And so there is an instance even with 2 players that both MMS is non-zero, yet one player must get a bundle that is worth 0. And in fact, we're going to see this example towards the end of the lecture. Okay, so this is maybe the most prominent relaxation of MMS in the literature. We offer a new relaxation, a resource augmentation approach. So basically what we're asking is, what if we could duplicate goods? How many goods would we need to achieve MMS? That's what we're trying to study in this work. And resource augmentation is a very common tool in beyond worst case analysis, both in C.
How many we would need to replicate? What is the minimum amount we need to replicate?
Yes, yes, yes.
So if you replicate everything, you just split it equally, that's it?
Yes,
You-
yes.
Okay.
But don't ruin the next slide for me, please. Yes, I will talk about it. Yes, definitely. Okay, so resource augmentation is a very common tool, both in CS and in economics, to study beyond worst case analysis. So two examples. One is so Kalyan Sundaram, I hope I'm pronouncing it correctly, and Proust from 2000 that show that if you slightly increase the speed of one of the processor, you can circumvent impossibilities in non-clairvoyant online scheduling. Another prominent result is Bureau Klemperer. I think I'll be the third person mentioning it today. So adding just one more bidder to an auction allows you to achieve optimal revenue with a simple mechanism. Duplicating goods actually also makes sense in some practical settings. So maybe there are settings in which duplicating goods is easy, like allocating courses to students. This is actually the original setting in which Budish presented the notion of MMS, and the idea of duplicating goods can be traced back to this work. Yeah, maybe we can use it to circumvent some impossibilities that I've just mentioned, and spoiler, yes. Okay, so let's try to be a bit more concrete about what we're asking. So what if we could duplicate goods? So as I think that's what Yossi was trying to say, that, well, if we can copy every good n times and give each of the agents the full bundle, then we can definitely achieve MMS regardless of the valuation. So great, there is already one result that we have, but what we want to ask is, what is the minimal number of copies, or what can you do with very few copies? Can you guarantee the MMS in the original market? What can you do for general evaluations, for additive, for anything in between? So first restriction, and this is for this talk, I'm mostly going to talk about settings in which we can only duplicate a good just one more time. Okay, so a good can appear in at most 2 bundles, no more. And we also restrict ourselves to cases where an agent cannot get 2 copies of the same good. Okay?
Cannot get or doesn't want?
Cannot get. Because
And doesn't want, because he doesn't.
Yes.
I don't know if he doesn't want. The thing is that the valuation function that you receive are only defined for one pair. They're not defined for 2 pairs. So I don't want to deal with that. So I'm just gonna.
It's like in course allocation, you cannot get 2 seats in the same course.
Yeah.
Yes, specifically, but with fruits that's not exactly. Yeah. So 2 seats in the same class will definitely give you nothing, but 2 pairs might. But I don't want to handle this question, so I'm just going to prevent that. Okay. So here's an example for allocation with 3 copies, right? So we allocated the 5 fruits, but we actually duplicated the apple, right? We gave the apple both to the cheetah and to the bear, the banana also. So 3 items were duplicated here. Again, no more than once. Okay, so in these settings, what are our results? So first of all, we show that you can achieve full MMS, and full MMS, I mean the MMS from the original market, with no more than the minimum between n minus 2 and m over 3 copies. So n is the number of agents, I remind you, and m is the number of goods. We can get an approximate MMS, so 5 over 6 MMS with n over 2 copies. And I remind you that the best without copies is just a bit more of 3 over 4. We also have a tight bound. Okay, so these first 2 are for additive valuation. Sorry, I haven't mentioned that.
Sorry.
Yeah.
N minus 2 copies means that you copy n minus 2 different items once more?
Yes, yes, that's exactly what it means. For general evaluations, we give a tight bound of m over e copies. So we show that m over e copies are sufficient, and there is also an example where this is necessary. Here we allow multiple copies of the same goods, and this is in fact necessary.
Not
We,
to the same agent.
not to the same agent, so duplicating some good more than once, allocating to different agents. And we also have a similar results to the first one for chores. So chores with additive valuations, we show that with n minus 2 deletions, you can achieve MMS. And, sorry? You delete chores, yeah, so this is like the analog. Instead of duplicating goods, you delete chores.
You do all chores but n minus 2.
Yeah, you allocate all the chores, but except for n minus 2.
It's not fair. If you can delete shorts, then you can.
N minus 2 deletions means you are left with 2.
And no, m is the number of goods, n is the number of agents. So number of agents minus 2 deletions.
It's usually true, like if m is smaller than n, then the MMS.
The MMS is 0.
Oh, okay.
So m is usually.
Yeah,
not
so you, yeah. And we also have some improved bounds for ordered instances, where ordered instances are those in which all agents have the same ordinal preferences. So they all agree that the banana is greater than the apple, greater than the blueberry, but the nominal valuations might change. So in this talk, I will be focusing on the first 3 results, maybe the full argument for the, yeah, so just a taste maybe of one of each.
Question about
Yeah, sure. Oh, sorry.
if n minus 2 is less than m divided by 3, so it does make chores, deletions and copies symmetric,
Sorry, if n minus 2 is smaller than m over 3.
then deletions and copies are symmetric in that case.
Yes, so actually it's the same argument that gives you n minus 2 for copies, give you n minus 2 for chores. The same algorithm, practically the same algorithm, up to like small difference. Yeah.
If you delete the shorts, you
Mhm.
compute the MMS according to the original.
Yes. Yeah, what we're studying is the MMS with respect to the original market. How can we achieve that with resource augmentation? Yeah. Okay, any other questions on the setting or the question?
But who does these chores?
You know, sometimes, you know, for fairness, for the sake of fairness, you have to, you know, keep the house dirty. I don't know, or something like that. Okay. Okay, so for the rest of the talk, we'll be covering 3 of the results. So for additive valuations, I will show the complete argument to how to achieve full MMS with n minus 2 copies, then maybe a sketch of the argument, how to get 5 over 6 MMS, and then the upper bound, showing how with m over e copies you can get full MMS for any monotone valuation.
If you allow more than 1 copy for each item, can it be better than n minus 2 total?
That's a very good question, and probably will. Oh, it does not appear in the last slide, but yeah, it should. We leave many open problems. This is definitely one of them. Okay, so let's begin. Okay, so first of all, and this is for the rest of the talk, I will assume that the MMS of all agents is normalized to 1. This is without loss. And note that this implies, as Alon showed for the 2-agent case, that the value of each player to the grand bundle is at least n, the number of agents, right? Because you have each player has a partition into n bundles. The minimal one is worth 1. And the evaluations are additive. So the algorithm is comprised of 3 steps. The first step, we will, if there are very good, very large goods, so a good that is worth 1 to someone, we will remove those goods along with one of those agents. We show that this is without loss. Then we will move to a matching stage where we try to satisfy some of the agents, okay, without copies. And then finally, we will move to a backfilling stage where all the agents that we were not previously satisfied will be satisfied now, but we might need some copies to do that. Okay, so first step, reducing the instance. This is quite a standard argument in MMS literature, and this doesn't really have anything to do with copies. So the idea is the following. Let's say we have a cheetah here which values the apple more than 1. We want to claim that if we remove the cheetah together with the apple, the MMS of the remaining players for the remaining goods may only increase. So solving this new instance successfully, so finding an allocation which achieves the MMS in this new instance, will actually could be mapped back to the original instance and give a fair allocation there. Okay, so basically what we need to show is that the MMS may only increase. So if this is the case, and the cheetah likes the apple more than one, we remove the apple and give it to the cheetah. Now we ask what is bear's MMS value in the new instance. Okay, so in the original instance he needed, right, in the original instance, this was the partition that defined his MMS. So one of these bundles is the minimal bundle, and it was worth, it's worth defining the MMS. Now, if we remove the apple, let's look at some partition of the remaining goods into two bundles, right? We can add the banana to the blueberry. Now we have some partition into two bundles, but this partition is such that the minimal value of this, of any of the minimal valued bundle here is greater than the minimal valued bundle in the previous one, right? Because the apricot and pear are obviously better because they also appeared in the last partition. Blueberry appeared in the last partition alone, but since we added the banana, we could, the value of this bundle may only increase. So we have two bundles here. Each of them is greater than the minimum. But this partition into two bundles is a lower bound for the MMS, right? Because the MMS is the partition that maximizes the minimal bundle. So what we get here is that the bear's MMS for two players without the apple is greater than the original MMS. And this is what we wanted to show. Okay? So from now on, without loss, I will assume all goods are worth to all agents less than one. Any questions about this procedure? Okay, good. Now we move to a matching stage. So now we want to satisfy as many agents as we can without copies. And the way we do it is we pick some agent, say Mr. Bear, and we ask him to give his MMS partition. So P1, P2, and P3 are Bear's MMS partition, and we look at the following bipartite graph. On the left-hand side, we have the agents. On the right-hand side, we have the bundles that Bear partition to, and we draw an edge between an agent and a bundle if and only if it satisfies this agent. So the value of this bundle to this agent is at least the MMS, at least one. So note two things. One is that Bear, by definition, is connected to all bags on the right-hand side. And second is, and this is by additivity, that each agent must point to at least one bag. Okay? Now we try to find a perfect matching here. If there is a perfect matching, as there is here, right, we can just allocate P1 to alligator, P2 to cheetah, P3 to bear, and we're done, right? Everybody got a bundle that they're happy with, no copies, we can all go home. That's great. But what happens if this is not the case? So if this is not the case, then there is some set of bundles that violates Holt's condition, right? So there is a set of bundles, P1 and P2 here, that consists of more bundles than the number of neighbors that it has. So here we have P1 and P2. There is only one neighbor, which is Bear. Okay. Now what we want to do is we want to take a subset of this P prime set, which is of size P prime minus 1. So just remove one of those bundles and match, and match P hat here, say P1, with just, with all its neighbors. So find a perfect matching between P hat and gamma of P hat. What this matching satisfies are two properties. One is that every matched agent is satisfied, right? And this is by definition because there was an edge drawn between the two. And second is because the number of bags here are the same as the number of agents here, every agent outside the matching did not point to any bag here, which means that any bag that was allocated, say P1 here, was worth strictly less than 1 to all agents who are unallocated. So both the alligator and the cheetah did not like bag P1, which was allocated. This means that the remaining value here is at least the number of remaining agents, right? Because for every agent that we've allocated a bag to, we've also allocated a bag which was worth less than 1. Okay? Good. So 2 properties, every matched agent is satisfied, the remaining volume of goods is greater than the number of remaining players. Oh, and one important thing to mention is that this matching is always at least of size 1, right? Because bear is connected to all the goods, there is always a matching of size 1. Good. So what we were able to do in the first 2 steps is to satisfy some subset n prime, some subset of the agents. We only have n prime agents left, and each of those agents left have at least a volume of n prime for the remaining goods. Now, in the last step here, we're going to satisfy everyone else. And now we're going to do bag filling with copies. So normally with bag filling, you just take the goods, put them in a bag until someone likes them, raises their hand, says, I like this bag, and then allocate the bag and continue onwards. The problem with this process without copies is that you can lose a lot of value, right? If you add a very good, fruit as the last good, then someone might raise their hand, but a lot of people would have liked this bag, and so a lot of people will lose a lot of value if you allocate this good. This is what we're able to prevent with copies. So let's see how we do it. So the first thing we do is, again, add goods arbitrarily. So we first add the banana, nobody likes the bag. Then we add the pear, still nobody likes the bag. But as soon as we add the apple, 2 agents like the bag, we allocate it to one of them arbitrarily. So let's say the alligator. But now, instead of starting with an empty bag, we duplicate the last good. So we start out with an apple in the bag, and then we continue. So we add the apricot, now only the cheetah likes it, we allocate to the cheetah, and then again, we duplicate the apricot, start the last bag, give it the blueberry, and now this is the last bag, we ran out of goods, we just allocate it to the bear. This is the entire procedure. What are the guarantees here? So it's easy to see that agent gets at most 1 copy of a good, so this is valid in this sense. A good is copied at most once, this is also great. And if we allocated t bags, we require t minus 1 copies. The question is, are all agents satisfied here? So do we have enough volume to satisfy all agents? And a very simple inductive argument shows that this is in fact the case. So what we want to show is that in each round t, if nt are the number of remaining agents and mt is the set of remaining goods, then the volume some agent has for all the goods is at least the number of remaining agents, right? And the base here is the guarantees of the matching stage. This is exactly what one of the properties that the matching stage guaranteed. And now let's look why this is true throughout. So let bt be the bag which was allocated, and g is the last good that was added to bt. Because nobody raised their hands before g was added, then we know that for any agent, vi of bt without g is strictly less than 1, right? What is the remaining, what is, for some I which did not get any bag, what is the value of the remaining goods? Well, what are the remaining goods? These are the goods we had at time t, minus what we allocated, this is bt, but we copied g, right? So this is still in the game. So by additivity, we can split those 2 apart. This is greater than nt by the induction hypothesis. This is smaller than 1 by the claim we just made. And what is nt minus 1? This is exactly the number of agents in this in the next round, right? Because in every round we just remove 1 agent. Good. So now we can conclude that we satisfied n minus n prime here. We are left with n prime agents in the bag filling stage. N prime minus 1 copies were made. And because we satisfied at least 1 agent in the matching stage, we conclude that n minus 2 copies suffice to achieve MMS. Okay, so this simple algorithm gives you n minus 2 copies and achieve the full MMS in the original market. And I'll just note that for n equals 3, this is tight, right? Because we have an example in which 0 copies are not sufficient, and we just show that 1 copy is sufficient. Okay? Good. Okay, so I will try to sketch how we give 5/6 MMS with just n/2 copies. So, so some things are similar, some things are different. So first of all, what we're going to do, and this is a standard technique when talking about MMS, is try to move from a general instance to an ordered instance. An ordered instance, again, is the one where everybody have the same ordinal preferences. They agree that the banana is greater than the apple, etc. And without copies, this is really a standard technique. It doesn't generalize us very well to copies, we think. So I may talk about this in a minute. But as soon as we moved to this ordered instance, now we're doing bag filling, similar to what we did before, but we don't just add goods arbitrarily. We do it in a snake-like fashion. So it's kind of bag filling meets round robin in some sense. After this stage, what we'll be able to do is we'll be able to satisfy most agents. So most agents will get something which gives them 5/6 MMS, and the rest will get 5/6 MMS up to 1 good. Okay, they will need 1 more good to be satisfied. And what we are able to show is that there is actually enough goods that people are interested in, so we can later match these n prime unsatisfied agents to n prime copies of different goods. And that way, we give each of them just 1 good and satisfy. Okay? Good. So, yeah, maybe I'll... okay, so let's see how we make an instance ordered. So, basically what we do is we need to kind of forget about the original setting where we have goods and move to a setting where a virtual instance where we allocate tokens instead of good. And you should think about a token as your queue number. So your queue number, if you have token k, this means you get the right to choose at the kth place in some picking sequence. How will that work? So we move to the token world in some way that I will specify in a minute. And let's say we have some allocation in this token world. So Bear got tokens 1 and 3, Cheetah got tokens 2 and 4. How will we map this allocation back to the original instance? We'll just let them do the picking sequence according to their tokens. So Bear will pick first. He will pick the blueberry because that's his favorite fruit. Then Cheetah will pick second. She can pick any fruit that is not yet picked. So she will obviously pick the apple, which is her best, most desirable fruit. Then Bear will pick again, pick the apricot, and Cheetah will finally pick the remaining pair. And what that gives you is that if you think of these tokens as your queue number in a picking sequence, then your value for token k is the value for the k most value group, right? Because this is like the worst case. This is what you can achieve in the worst case. And any allocation, and note that any allocation in this token world, according to this valuation, can only be improved when we go back. This, right? The Cheetah here thought she would get blueberry and pear. In fact, she got apple and pear. So her situation actually improved. Good. So this is how you order the instance and how you map it back to the original. And now let's talk, let's assume that we have mapped the instance to the token world, to the ordered instance. Now let's see how we allocate the tokens to achieve 5/6 MMS for most agents. So first we initialize, okay, so we think of n bags, okay, B1 through Bn, and we initialize the bag k with tokens k and 2 to the n minus k. So this is how it's going to look like. So this is the initial, this is the initialization stage. Now, If there is some agent which likes a bag more than 5/6, we allocate it to him. So if the cheetah likes B2 better than 5/6, we give her the bag. If not, if no one likes it, no one likes any of the bags, we continue to fill the bags with tokens, but we do so in a snake-like manner. So now we give 2n plus 1 to B1, we skip B2 because it was already given to cheetah, and all the way through Bn, and we continue onwards in this snake-like fashion. So this is why I said like bag filling meets round robin, right? Because we kind of round robin over the bags. And eventually, if we ran out of tokens, we just assign the remaining bags to agents in some arbitrary manner. Okay? Oh, sorry. Okay, and as I mentioned earlier, going back from tokens to goods is simply done using this picking sequence. So if we have, and as I said, your condition can only improve, right, when you move back to the world of goods. So if the cheetah was happy, she got a bundle she was happy with, she's still happy. If the bear was not happy, he might still not be happy when we move back to the world of goods. But what this snake-like bag filling stage allows us to show is that, well, he's may not be happy, but he's not happy up to one good. So there are a few tokens that if he would get them, in addition to what he already has, he will surpass the threshold of 5/6. And when moving back to goods, we would also like to move this wish list also back to goods. We would like to map it back. So we did so with the tokens in the bag that he got. Now we would like to do the same with the tokens. So what we would like to do, right, if we could give him one of these tokens in addition to the fruit that he already had, then we would be done. However, it might be the case that the tokens that he had in mind, right, so here he would be satisfied if we would give him token number 1 or token number 2. In the world of fruits, this means if he would only give me one of my 2 favorite fruits, I would be happy. But what if he already picked his 2 favorite fruits in this picking sequence? Then we need to do some so we need to do some fix in order to map this set of tokens to a valid set of fruits. So I'm kind of lacking the time to get into the specifics, but we use some kind of an augmenting path fix to have a set of wish lists that we can actually give him in this new fruit world. Okay, so I have like 5 minutes. Okay, so yes, so I won't be able to show why this is true. So why most agents are satisfied and those unsatisfied agents have a long wish list of tokens that they'd be willing to accept, but those 3 stages together give us the conclusion that n over 2 copies are sufficient to achieve 5/6 MS. Okay. Lastly, I will talk about general evaluations and why m over e copies are sufficient. Okay, so up until now we've discussed mostly additive valuations. Nothing has really changed. We think about monotone valuations and we define the MMS still in the same way, so partition into n bundles, etc. Here's what we show. That given an instance with general valuations, monotone valuations, there exists some partition such that each agent is satisfied, gets at least his MMS, the total number of copies is at most m over e, and some goods can be copied many times. Okay, this is unlike previous results. Okay, so let's give at least a sketch of this argument. So let's look at some agent, say the alligator, and look at this MMS partition. We're going to look at the allocation which assigns one of his MMS bundles to him uniformly at random. Okay, so just one of his MMS bundles uniformly at random. We're actually going to do the same for all agents, And what we give is a probabilistic method argument. So what we show is that in this allocation, where each agent gets one of his MMS bundles uniformly at random, the expected number of copies is M over E. Thus, there must exist some allocation in which there are at most M over E copies.
So it's not constructive.
It's not constructive.
Finding the MMS allocation is
Yes.
not going on.
Note that it's not constructive and computationally hard because just finding an MMS allocation is computationally hard. Good. Yeah, so I have like 2 minutes. So so this is a very simple argument. So this is a very simple argument. The main observation is that the probability of a good that you allocate a good to some agent is 1 over n, because it only appears in one of the MMS bundles. With that observation, you can pretty much do the math yourself and show that the number of items, the expected number of items including copies is m. The expected number of unique items allocated is 1 minus 1 over e times m, where m is large enough. So for like in the limit. And so the expected number of copies by linearity of expectation is m over e. Good. And there is also a matching lower bound. I'm just going to say one word about it. So there are instances in which m over e copies are required. And the intuition is from this simple instance here. So we have 2 players. Bear is the column player. Alligator is the row player. There are 2 bundles in which they're interested in, and this is also their MMS partition. So bear only likes banana and apricot together, or blueberry and apple together. Note that this is also the hard instance for alpha approximation, right? So let's say we want to give bear some non-zero bundle. It must be one of the 2 columns, and this will prevent us to give any non-zero bundle to the alligator. So this shows that for monotone valuations you cannot achieve alpha MMS. And also, right, and so without copies you can't really do anything. However, if you allow copies, then just here 1 copy is sufficient to give both players their MMS. So indeed you should think about it as an example with n over 2, m equals 2 to the power of 2, and m over 4 copies are required. If you generalize this example to the n-dimensional cube, you will get this. Okay, some simple counting argument will give you this. Great. So a little bit over time, but let me just repeat quickly on what we saw today. So we saw a fair division framework, a new fair division framework for allocation with copies as part of the resource augmentation approach. How to get for additive evaluations with n minus 2 copies, how to achieve full MMS, and 5 over 6 MMS with n over 2 copies, and we even saw this m over e for general evaluations. I already mentioned the other results, so let me quickly say something about open problems. So there are really a lot of open problems. This is just a partial list. The holy grail in some sense is, can we get MMS for additive evaluations with a single copy? So for now, there is no reason to believe this is not true. That would be awesome. A first step will be to find out the correct number of copies for n equals 4. So I mentioned that for n equals 3, 1 copy is sufficient, and we show how to do it. But for n equals 4, we're not sure if the real number is 1 or 2. That would be great to find out. We have results just for additive and for monotone. Getting results for the rest of the complement-free hierarchy and other classes evaluations will be great. And also applying the resource augmentation approach to other fairness notions. Also a great idea. Yeah, that's it. Thank you for your attention.
Quick question as I set up the notes.
Yes. Yes.
So, actually, if you're having extra copies, it's not clear why you're competing against the MMS. For example, you could compete with fair share. Actually,
With proportional, you mean?
proportional.
Mhm.
Actually, if you allow to copy an item more than once,
Mhm.
I think there is like a trivial proof that with n-1 copies,
It
you can
can
get
be-
actually your fair share.
for the same item, but
The same item,
Yeah.
but
Yeah,
overall,
yeah.
But you-
just,
but not
just
distinct,
do
it's
round
tight,
robin
yes,
and ask
yes.
for the first item to
Yeah, yeah.
duplicate.
Yes.
So it's, you get much better results. I mean, you compare it to fair share, not to MMS, which is
Fair
much
share, you
better.
mean proportional?
Proportional,
Yes.
but you may copy the same good.
the same good multiple
Yeah,
times, but
but
the total
it's-
number of copies is still, it's still only the same, it's
If
n-1.
you restrict to
Hmm?
sorry.
No, בבקשה.
No, if you restrict to one copy per good, then you can't get it. Like if you, let's say,
Yeah.
cannot
I
double
mean,
the.
why do you specifically strict with one?
No,
copy?
say you have one super good, which is really very.
Really good. Yeah.
Which one of the two?
Yeah.
Okay,
אבל זה משהו הרבה יותר חזק. עכשיו בסדר, אתה מקבל מול הפייר שייר, לא מול ה-MMS. הפרופורשיונל שייר הוא יותר חזק.
זה רק נכון באדיטיבי.
זהו, כן, יש גם שאלה מעבר לאדיטיבי.
כן, זה לאדיטיבי.
יש
בהחלט, זה לאדיטיבי, אבל זה פשוט, אתה משווה מול משהו הרבה יותר חזק.
עם הקופיס?
משהו חדש כאילו. זאת שאלה מעולה.
זה נשמע אימפוסיבל.
כן, למה
אה,
דווקא...
אני לא מתווכחת, פשוט אני צייתנית, אני פשוט מגנה על
כן.
Okay, so
איזה קופי אתה...
okay, so we have the so this is the last of the day, and afterwards we have a reception downstairs, and we have the Yaakov Tachman from Yaakov from Judah Stock on constructive records.
Okay, thank you. So the talk will have two parts. In the first, I will show you what I mean by constructive vectors theorem. And in the second, I will show you some somewhat surprising properties of this specific construction that we have in the instance. Okay, so let me start with the definition of majorization. We have two real value distributions. For simplicity in this talk, I will bound the support to be in the segment 0, 1. You can, all the results are generalized for distributions over the reals with finite expectation. But for the talk, I will say that the support is on 0, 1. And capital F and capital G are their CDFs. I will, throughout the talk, I will identify distribution with its CDF. And you can look at the integrated CDF. And this will be denoted with hats. So there is this property that the integrated CDF of F is smaller than the integrated CDF of G, point-wise for all points, and this is essentially a requirement that the expectation equals. Okay, so this is the property of majorization. To see how fundamental this notion is in economics, we can just look at how many different names it has in the literature. So majorization, second order stochastic dominance, mean preserving spread. It also called the convex order, because for every convex function it preserves this inequality for the expectation of every convex function. Lorentz order is also because maybe he was the first to really do it. It's also less risky in the context, if you think of this as distribution of gamble that you get, and more in the context of this talk, you can also view it as less informative signal, or less informative information about something, namely that F is less informative than G, and I will explain why it's essentially means that.
Smaller is majorized. I would expect major to be.
So I think in Lorentz the property of being concentrated around the mean was a good something good. Yeah. So, like, right? If it's a gamble, you want it to be as concentrated around the mean. If it's an information,
is
you
the
want it.
best.
Yeah.
Constant is the best.
Yes.
That's the.
But in information, it's the other way around, right? Less informative. You want to get as much information as possible.
Constant
Whereas,
is majorizes everything.
okay, so this is, now let me say what is a signal. So we have, now think of this distribution as, let's say, prior. We have a real value state that is drawn according to this distribution. You have an abstract set of messages, let's call it calligraphic S, and a signal is essentially a noisy information about the state that, that is a mapping from the realization of the state into a distribution over the signals. Okay? This is the garbling of the information that you receive, or in other words, a noisy signal. The induced distribution of posterior means, right? After I got some signal S, now I update my posterior belief about the real valued state, and here I specifically interested not in this entire distribution, later we will be interested also in the entire distribution, but currently only interested in the posterior mean of this distribution. So every signal induces some distribution of the posterior means, and let me give you an interpretation, a possible interpretation, though it's not mandatory, but let's say that we have two metastates, high and low, and we have some partially informed agent, call him a sender, who receives partial information, and here theta now can reflect the posterior of the sender after observing this information, right? If it's only a binary state, then posteriors are numbers in 0, 1, and pi can be, let's say, a policy, some signaling policy of the sender. And now you can see that a Bayesian agent who observed the signal S, his posterior will be exactly this expectation, and this is why posterior mean is a kind of natural candidate natural object to consider in this context.
What is G?
Capital G?
Yes.
It's a distribution over 0, 1. You can think of it as a real valued state and the prior over this real valued state.
The CDF.
Yeah. What is Blackwell's theorem? Blackwell has many theorems, but this is one of them. Yeah, the Blackwell's theorem of this talk is the following: that F majorizes G if and only if there exists a signal that induces distribution of posterior means F. Okay, from the prior G. From the prior G.
From the prior G.
Yeah.
It's missing there.
Yeah. The original proof of Blackwell in 51, so one direction can be proved by Jensen's inequality argument, and the other direction is more involved, that is based on duality, and it's non-constructive. It doesn't tell us how to construct a signal for given a pair of majorizing distributions.
Can you give more intuition? What signal exactly do you need? So you have S, which is closer to the mean than G.
All the talk will be about it. This is exactly.
He's going to construct it.
Yeah. I'm going to construct it, and then you will.
Okay, but what exactly do you want to construct? A signal that what?
Wait a couple. Okay. So our contribution is a constructive proof of this direction, namely. We get an input of two distributions for which we know that one majorizes the other, and we will construct the signal.
I think in fact, you should answer him. Or maybe I should answer. No, it's not very helpful. No. So here it is. Suppose you had a prior of 1/2, okay? Now, take the, so prior 1/2 fixed, okay? Now look at the 1/2 on 1/4, 1/2 on 3/4. That's a posterior, okay?
Oh, no,
How do you generate those posteriors
Sergio,
from 1/2?
This is the next slide. Okay. Okay. Not 1/2. Okay.
I mean,
Here
I
is-
just, for some,
no, but this
to
is
have-
exactly what I have in the next slide. Okay.
How do you get the equal?
Here is an example, okay? You have a distribution. One of them is beta 1, distribution. What is important, which has this density. The second distribution, G, the more informative one, is uniform over 0, 1. Okay? So according to the pictures, you can see that the red distribution is more concentrated in some sense around the mean. So it is less informative than the blue one. And what Blackwell's theorem tell you, look, do 2 integrations to these functions. You will get these 2 drawings. And you just need to check that G point-wise is above, G hat is point-wise above F hat. And it means that there exists a signal that induces F from G. The question that I want to ask, even in this specific example, how to construct such a signal? What will be a signal in this context? It will be something that gets as an input for every real value the realization of state. I will do some lottery and report an abstract signal which a Bayesian agent, by deducing it, should result in this distribution of posteriors. Okay?
What do you mean induces F? You mean that a Bayesian agent, if he starts from a prior G and gets a signal, will have a
No, he doesn't. He knows the prior G, but he doesn't know the realization. The informed agent is the sender who knows the realization of G. He just gets a signal, computes his posterior mean or his posterior about a binary state, it's equivalent, and all this procedure will lead him to each one of these posteriors with these densities.
Okay, so you can set a signal in order to convince a Bayesian agent to have a more concentrated posterior.
Yeah?
But for every realization, the receiver will have a different posterior, right?
Yes.
Okay, so what is the F function? Is it like the expectation over?
Yeah, I said posterior mean. For each one, this will be the distribution of the posterior mean.
Okay.
Okay? But as I showed in the previous slide, you can think of it as a binary state environment in which his actual posterior about the binary state will be this number. Okay?
What is the input to your algorithm? How do you get the input?
Okay.
In the discrete case, it's a trivial problem, right?
Not necessarily. I mean, you can come up with algorithms. Not necessarily. I mean, you can. No, even you can solve it with linear program. Yes, you know it has a solution. But to say exactly what it is, it's not a trivial problem, I think.
It's a system, not enough. It's a system of linear equations. That's it. You don't need linear programming for that. You just need vector matrix in the worst case. Maybe I'm wrong.
The way I see it, you need weights, right? You alpha ij, and you want you have a system of equations.
Okay. Well,
Yeah.
no.
Yeah, but.
Okay, in the worst case, it's a linear program.
Yeah. Okay. So let me show you a class of signals. We call them downward uniform signals. So how they look like? They are specified by a single monotonically increasing function h. Okay, this is a monotonically increasing function, And if the state is theta, then what I'm doing as a sender, I'm drawing uniformly at random a signal from 0 to this h of theta. Okay, and this is what I'm sending to the receiver. Okay? It's specified by a single monotonic function. Now let's just think of it from the perspective of the receiver who just got the signal. He said, okay, I got the signal. Where can I get it? I can get it in over this line. So you can think of it that he essentially has this lower bound on the state. Okay, so here is a theorem. If f majorizes g, then there exists a downward uniform signal that induces the distribution of posteriors f. The difference between this and Blackwell's theorem is just, I added these two words, downward uniform. So far, the proof is not constructive because I didn't tell you what h is, right? I just told you that it's still non-constructive proof because I didn't show you what the function h is, so let me tell you what the function h is. So this is the picture of the CDFs. Alpha that is written here, you can think of it as the difference of these two slopes here, right? You have this slope and the red slope. So alpha essentially is the difference of these two slopes, and the function h turns out to be
Those are the f hats.
f
So
hats.
F
This
and
is
G are
a
the
picture in the
derivatives.
integrated.
So the derivative of f hat is big
Is
F
F,
and
yeah.
g hat is g.
Yeah.
That's why I say the slopes. So it's a difference of the slopes at capital T minus T. What's capital T now?
Capital T is you take this point, you take the tangent, and at some point this tangent will intersect
Oh, I see. That determines-
the red function.
I see. So,
So this
capital
is
T
the
is a function of small t.
Yes.
For every small t, there is a capital T for which
Yeah.
you look at this
Yeah.
at the red slope minus
Yeah.
the black slope.
Yeah. So you have the alpha function, and now from the alpha function you can deduce the h function using this formula. You need some integration, but okay. But a closed formula. Okay. Let's go back to the example that of the beta and the uniform. So it just shows you that so first we need capital T of t. We calculate it. Yeah, it's just basic calculations. From this we deduce alpha t, and then we integrate and we get that h of t will be t to the power of t squared t. Okay, so the answer to the original question, how to garble the uniform information into a beta information, here is one suggestion. You can use the downward uniform signal for the specific function h equals t to the power of 3 over 2. Okay? Another example. Let's G still be uniform, but now F will have two atoms. One atom at 1/3 and of weight 1/2, and one atom at 2/3 again of weight 1/2. You can do the calculations and see that the distribution that will be the downward uniform signal, essentially what it has to do. So what you see here in the picture is the density, right? If G is uniform, so the density of the uniform is constant. So you can draw it in a rectangle, in a square. And what I draw here is which mass I map into the atom of 1/3 and which to the atom of 2/3. And the crucial property is that the mean of the red area, which can be crazy area, but not in this, should be 2/3, and the mean of the blue area should be 1/3. Okay? So it turns out that what the downward uniform signal will do in this case is captured by this figure. Okay? I want to highlight that there are other ways to garble information into 1/3, 2/3. This is definitely not unique, and in fact, it's typically, or in only in very extreme situations, there exists a unique coupling. Typically, there are a lot of them, but
So, just a second. So in that case, if you get x between 0 and 1/3, then you do uniform on 0, 1/3.
so h. I didn't draw you h. The h function.
No,
the
but
h
I'm
function will be
interpreting.
a two-step function.
So the h function is 1/3 for x up to, right? For x between 0 and 1/3, it is 1/3. Do I understand it correctly? So your signal is going to be uniform between 0 and 1/3 for any x which is between 0 and 1/3. And then when you are above 1/3, with probability, I don't know, 1/4, 3/4, whatever,
It's going to be a two-step function with a jump exactly at the point 1/2,
yeah.
and with different levels, in a way that that will exactly create. Yes.
Maybe I didn't understand correctly, but in this example, does G does either one majorize the other? Because I think F had of 1 and G had of 1.
F is the less informative one, right? You can contract, you can see it in this picture, that you can contract the information of G into these two atoms, right? Here is one example of how to do it. Take all this red mass and contract it to 2/3, and take all the blue mass, which automatically you don't need to do the calculation for the blue mass, because if this one is contracted to 2/3, you just should check that the area of this square is 1/2, and it is. Yes?
So is there a specific reason to use thirds or to put in a special emphasis on thirds?
So we suggest one specific signal, which is the downward uniform signal, which creates exactly this garbling. There are infinitely many others. Okay, here is an example of another option. You can take, for instance, all this to contract all this segment of length 1/2 into 1/3, and the remaining to 2/3. Okay, and you can draw crazy pictures, and you can see that you have quite a lot of flexibility in it. This raises.
Why do you say garble?
This is the name of garbling information, making it more noisy, kind of.
1/3, 2/3 is more noisy than uniform 0, 1?
Yes. Yes.
I mean, you replace 0, 1/2 by just 1/3. Previously, you could distinguish between all the numbers between 0 and 1/2. Now you just get their average, which is 1/3. That's all you know. Much less information.
It's not exactly. No. This was for 1/4 and 2 3/4.
I just want an example.
It's like the privacy mechanisms where you take information, make it like noise in order to make it more private, to avoid leaking it.
Maybe. Okay. So what is special about the specific right? So every signal that you will design will essentially create you some correlation between the distribution G and the distribution F. And what I want to ask is
Between theta and S.
between
It's not a
theta.
correlation between the margins. Those are the marginals.
Exactly. No. The joint distribution
Yeah, okay.
of F and G. Yeah.
No, sorry.
The correlation of the
Take it
pair
back.
F and G, and every signal might induce something different. Like we see in this picture, it will create different correlations between those two. And what I want to ask is what is special about the one suggested by us. So one answer can be, look, you have an explicit formula for that, and we don't know about explicit formulas for others, which is nice, but let me try to convince you about other interesting properties of this correlation. Let me tell you a story of persuasion. You have low state, high state, you have a partially informed sender whose initial belief, whose belief is whose belief is theta, drawn according to G, and we have a less informed. Typically, in persuasion literature, the standard assumption is that the receiver is not informed at all. I want to think of a receiver who is partially informed as well, but less informed than the sender. Namely, his initial belief is F, and F majorizes G. Namely, F is less informed contains less information than G. Sender reveals information over time. So by some continuous time analog of the splitting lemma, you can identify policies of the sender. Right, the only relevant parameter is the posterior of the receiver during during the time. So you can identify with continuous time martingales with initial distribution F, because it starts with F, and terminal distribution, which is not more informative than G, because the sender cannot reveal more information than he has. Okay, so henceforth we will talk about when I say policy of the sender, I will just say martingale. It will be the same. Let's say that the receiver has some irreversible adoption decision. Okay, you may think of it like taking a vaccine against corona, right? If you took it, it's irreversible. You cannot. Oh no, you know what also, buying a product sometimes is irreversible decision, typically. And the sender has a simple goal, just to persuade the receiver to adapt. The receiver has...
Not taking, by the way, is reversible.
Hmm?
Not taking the vaccine is reversible.
Is reversible. Yes, yes, yes. Yeah, when I say that the adoption decision is irreversible, I mean that, yeah. Receiver has a threshold tau above which she prefers to adapt. You may embed it in some binary state utilities that will get exactly that. And here is something which you should have in mind. I want to think of a situation in which sender does not know this threshold. Namely, I'm facing some
It's a threshold of the posterior, I guess.
Hmm?
It's a threshold of the posterior.
Yes, 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 yes. Everything in the language is, yeah.
So if the posterior is above theta, then I should
yes,
adopt.
yes,
If it's not,
yes.
I should not. Okay.
Okay. And here is a somewhat weird assumption, but not so much. So receiver, let's assume that the receiver adapts immediately at the first moment when his posterior passes tau. First of all, let me say why it's weird. He gets more information. Why shouldn't he wait more? He can only gain from it. So you can, if you think of a model in which the sender is, the receiver is impatient, namely he has some discount factor, and the sender is patient, he doesn't care when the receiver will take the adoption action, he only cares about that he wants to maximize the probability that he will take it, then what the sender can do, he can reveal information very, very slowly, so that in a moment when the sender's posterior is epsilon above tau, you say, okay, it's better for me to take the vaccine shot now, because the next time I will know something, my discount factor will be so slow. So if you want, you can rationalize it, but or if you don't like this rationalization, just take it as a behavioral assumption that at the moment when the posterior passes theta, he adopts. What we will see, first we will see that in this setting, I didn't say anything about the correlation of F and G, and so the first observation will be that the correlation of F and G plays a crucial role. This is something not, I don't know how obvious it is from from the description of the setting. And typically in persuasion problems, we didn't see cases in which the correlation was crucial. We will see that here it is crucial. And if the sender is the one to design the correlation, then the downward, he should choose the downward uniform signal correlation.
So this is downward because the condition is xt above something. If the condition be xt below something, you take the upwards, probably the symmetric one. You do
Yes,
the upwards,
yeah.
That's why.
The analogy of this.
There is an arbitrary choice because you could invert everything. You could take 0, make 1, and 1 make 0.
You just need to make the, you still take downward uniform, but you take H to be monotonically decreasing instead of monotonically increasing, and then this is what will create. Okay. Let's solve the problem for exogeneously given correlation. The sender does not control it, it is given. So if you want a model in mind, think that there is some public signal that distributed according to F. This is something that the sender and the receiver observe. And thereafter, there is one additional private signal for the sender, which generates G from F. And the sender has no control of it. This is what it is. And let me suggest a policy for this setting. A gradual revelation of bad news. What it says, look, I will tell the sender if at time t, I will tell if the realization is in the segment 0t. If my realization, namely of the sender, is in 0t, then he will know precisely the state. But other than that, I do not reveal any further information. Okay, so this is, it's actually what you are doing. You gradually reveal the worst news that you have so far, so it's a gradual revelation of bad news. Here is a proposition which is essentially a result by Dubins and Gilad. That's David Gilad and Dubins.
Dubins is Dubins.
Yeah, Dubins. And Gilad is Gilad. So for every given correlation, this policy is the best one simultaneously for all thetas. Namely, you don't need to know the threshold. This is the best thing simultaneously for all the thresholds. As you can imagine, neither Dubins nor Gilad, I think, their main interest was dynamic persuasion setting. They were interested in something else. So what they were interested in is on the distribution of the maximum of a martingale. That there is one-to-one correspondence between adoption in our setting and the fact that the maximum passes the threshold tau because of the immediate adoption assumption. Okay? So what is the result of Dubins-Gilad? The result is that, think of a Dirac measure F, namely not as we have just a distribution, but a Dirac. Then the gradual revelation of bad news induces a martingale that is a maximal maximum martingale. What is maximal maximum? If you look at the distribution of the maximum of this specific maximum martingale, it is better, and this is why it's maximal, than any other. In which sense better? In the strongest possible sense. First order stochastic dominance. Okay, the distribution of the maximum of this martingale, first order stochastically dominates the distribution of the maximum of any other martingale. And this is why we have this strong result of simultaneously for all thetas. The fact that such an object exists is somewhat surprising. Once you see it, it's maybe not so much, but yeah. Okay, so this was the. So what we need for this proposition is just to apply this for every point-wise. What I mean point-wise for every, let's say, realization of the public signal. And so this is essentially a proposition of there. Okay, so now we know what is the best policy, and let's just compare what's going on with in our suggested downward uniform policy versus just this arbitrary one. Here is the picture. What I draw here is, as a function of the threshold, what is the probability of adoption? I want to maximize it. Okay, so the green function, you can just trace for this dynamic revelation and see what is right to compute these probabilities. It's not very hard, and you get that this is the green function is the probability of adoption for the downward uniform policy. The black one is the probability of adoption in this for this correlation. Okay, so what we see in the picture, correlation matters. If theta is no, if tau, the threshold, is somewhere here, by the green correlation, by the downward uniform correlation, you get something that is better than by this second option. Okay? Yes?
This really looks like a lot like an inversion of the plots you had for f hat and g hat, where you had with the tangents from one to the other. It's like you had this referencing point at the same point, and then there's a gap in the middle, and it just looks like if you were like that, it just flips over when you talk about the correlations.
No, it is so.
It's
It's a it is a different graphs. I don't think there is over there. The functions always were concave or convex, and here, though, as you can see, even those can be arbitrary functions, non-convexity.
The evolution is what are they? It's the same. It grows. It reaches the maximum, shrinks again, and then ends the same.
Look, so one thing that is at least from that, in principle, if you will take just two distributions here, two different correlations, you might get a lot of intersections, and sometimes for some thresholds this one is better, and for some thresholds the other is better. The fact that we didn't get it here, I think it is quite surprising.
And the green is the maximum of anything you can get. That's a theorem.
This will be the theorem. Yes.
Anything that you put, it will always be below the green.
Exactly that. Yeah.
Yeah. Okay.
Exactly
So,
that plot.
so here are two things, a proposition and a theorem. Let's start with the proposition. It says that for no matter what the correlation is, and no matter what your policy is, in particular, you know that the best one would be to pick the gradual revelation of news, the probability of adoption will never exceed this term. What is this term? I'm getting back exactly to the picture that I had at the beginning of the talk. It's exactly the same picture, so, but I just renamed, here it was capital T, now it's tau, and here it is T of tau. So the probability will never exceed 1 minus G of T tau. So, and this is a global upper bound on the probability of adoption, no matter what the correlation is, and no matter what
So for
the
every
policy
tau,
is.
you look at G and you draw the
Yeah, now I
tangent
do.
from
Yeah,
there
exactly.
to,
Yeah.
to F.
Yeah,
G
yeah,
and-
yeah.
Whatever, and that gives you the
Yeah, I'm-
construction.
Exactly. I'm doing the tangent from this point to this function, and the theorem, which connects somehow the downward uniform signal to our, that the downward uniform signal achieves this bound for all thetas, for all tau, for all taus, and the correlation. Notice that neither the correlation of the policy nor the policy depend on this object tau, right? Because the correlation is, I said, downward uniform signal. There was no tau in this story, and the gradual revelation of bad news also something that is was not tau dependent. And in particular, this policy is the optimal policy. Even if I don't know tau, even if you have a population of agents, each have a different tau, it's universally best for all these cases. Okay, so in the 5 remaining minutes, I want to show you. I don't think I will have time to show you the proof of the theorem, but let me show you the proof of the proposition, or idea of the proof, because I think it's nice. So the first key idea is to do a trick and consider a static interaction instead of dynamic one. So consider a static interaction
So go directly to x1.
In which now tau is known to the sender, right? I'm giving him more power. And she reveals information in a single round, not as a martingale. It's hard to analyze what happens in martingales. It's much easier to analyze what happens in static interactions. And the key observation is the value of the static problem is an upper bound on the value of the dynamic problem. And this follows from just some reduction. If in the static problem the sender, because one of the things that the sender can do in the static problem is to say, look, what I'm going to do is I will run a martingale and I will reveal you whether it visited the interval tau 1. If it visited, then by the martingale property you can see that actually the receiver best action is to adopt. And so this is so what we want to do
So
is
the
to
stopping time when you first cross the interval.
yes,
And that's your signal.
yes,
Yeah. It's not your static signal.
yes.
Right.
Maybe it never happened and then
Okay.
okay. So now let's analyze this static interaction. So what is the maximization problem of the sender? Focus meanwhile only on this part. So what is the action space of the sender? It's no longer a martingale. He just needs to pick a distribution H. What this distribution should satisfy? It should be more informative than F, but less informative than G. He cannot reveal more than he knows. Okay? And you can also write in terms of H the probability of adoption, which is just 1 minus the CDF, right? Because we want above H and not below H. This maximization problem, you can also write it in the integrated CDF space. What I'm doing here is just translating everything to the language of the heads. So this will be just a point-wise maximization. It's just, this is my objective. And here, when I write derivative minus, I mean the left derivative. It is crucial that it's the left derivative, right? Because it might play a role if we have an atom at this specific point, and in the solution we will have an atom in this point. And the nice thing is that this problem is sufficiently simple to be solved explicitly. We have two of the lines, F and G. G is above F. Our freedom is to choose some convex function in between them. And we want it, and what we try to minimize, right? When you maximize this, it's essentially the left derivative at this point. So what will be the solution? You want to go as low as possible, and at this point to go as high as possible. And this is, you can show it formally that this is the solution. And now you also see the connection with everything, why the picture, this is essentially the picture that we have. Okay, I wouldn't, I will just say in one that what actually happens with this specific correlation in the gradual revelation of bad news policy is that at time t, you implement precisely this distribution. And this is why you essentially achieve it. This is it. Thank you.
Maybe one question before we head to the reception. Let's get the reception.
Okay, so let me just say thank you again to all of the speakers of today. And also big thanks to the Institute for Advanced Studies and all the people involved